Welcome back to The Explainer. So, if you're involved in agriculture, ag tech, or investment, you already know we are standing on the edge of a massive transformation. Today, we're unpacking a total paradigm shift. It's being driven by macroeconomic pressures from above and microscopic ecosystems from below. We're talking about a fundamental rewriting of how we grow our food, moving completely away from chemical dependency and toward genuine biological resilience.
Okay, let's dive into this. On the agenda today, we're covering modern agriculture's limits and market trends, an entirely new concept called the plant Holobiont, the key role of archaea, how it actually controls bacteria, the real-world benefits of core B&I technology, and finally, tech differentiation in next-gen agriculture.
Starting off with Section 1, Modern Agriculture's Limits and Market Trends. We really need to look at the macro picture first to understand exactly why agricultural stakeholders are scrambling for new tech solutions right now.
Let's talk about 14.7%. That is the projected compound annual growth rate for the agricultural microbial market. To put that into perspective, by 2030, this sector is projected to hit an insane $18.7 billion. For the executives and investors tuning in, this is a massive, flashing signal. Capital is moving incredibly aggressively toward biologicals. But you might be wondering, why exactly is this market blowing up so fast?
Well, it basically comes down to some unavoidable structural drivers. You've got intense regulatory pressures and massive corporate sustainability goals that are literally forcing the market to ditch chemical fertilizers. Take the EU's farm-to-fork policy. They are demanding a massive 50% cut in chemical pesticide use by 2030. That is huge. Add in retail giants like Walmart enforcing zero residue mandates for thousands of their suppliers, and a tidal wave of VC funding, the industry has absolutely no choice but to pivot.
Because the reality we're desperately trying to escape is the dependency trap. Modern agriculture is caught in this vicious, expensive loop. Farmers are overly reliant on costly imported chemical fertilizers, but dumping those chemicals on fields severely degrades the soil and wipes out vital microbes. That dead soil makes crops incredibly vulnerable to disease and drought, which tanks yields, kills profits, and creates this desperate demand for, you guessed it, even more chemical intervention. It is totally unsustainable. Moving to Section 2, a new concept, the plant holobiont. To actually break this dependency trap, we need a complete biological paradigm shift. We have to zoom in from that macro market perspective and rethink how we fundamentally perceive plants in the field. There is a stark contrast between the old way of thinking and the new reality. The conventional view treats a plant like a solo act, an isolated, standalone genetic entity. But the new paradigm? It's all about the plant holobiont. A plant isn't alone at all. It operates as an inseparable partner with a vast, complex microbial network in the soil. They function together as one unified, incredibly resilient system. You aren't just seeding a plant anymore. You are optimizing the entire holobiont ecosystem. It's a real game changer.
Which brings us to Section 3, the key role of archaea. Let's go even deeper into the microscopic level to meet the absolute star player of this unified ecosystem approach.
We really have to draw a hard line here between two totally different domains of microorganisms, archaea and bacteria, written as psychein in Japanese. While psychein handle the bulk of everyday metabolic tasks in the soil, archaea, which actually evolved to survive in some of the most extreme environments on Earth, act as the master network regulators of the whole community. They aren't just a subset. They are entirely distinct entities that serve completely different, crucial ecosystem functions.
And it's through niche differentiation that we see exactly how they interact. Archaea don't just aggressively wipe out bacteria. Instead, they beautifully manage the balance. They compete for resources like ammonia, but thrive in totally different conditions. Archaea love low-concentration, nutrient-poor areas, while bacteria absolutely dominate the high-concentration zones. By naturally coordinating the environment like this, archaea keep the whole system balanced, which, amazingly, also cuts down on harmful greenhouse gas emissions like nitrous oxide.
All right, Section 4, how archaea controls bacteria. Let's look at the actual mechanics here. How does this archaea regulation actually benefit the soil in real time? It is all about this incredible control valve mechanism. Think about it. Without archaea, as bacteria break down organic matter, their own waste products, things like hydrogen and ammonia, start building up until they actually stall their own activity. The whole decomposition system just grinds to a halt. But throw archaea in the mix, they act like an open control valve. They absorb and use up that bacterial waste. By constantly clearing out this metabolic trash,
Archaea ensured the bacteria never have to hit the brakes. They can just endlessly decompose matter and enrich the soil. It's a gorgeous, continuous loop of natural fertilization. Let's move to Section 5 and see how this builds into the benefits of core BNI technology. We are taking this control mechanism into practical field applications with a massive breakthrough known as biological nitrification inhibition, or BNI. When comparing a standard environment to a BNI-optimized one, it is completely clear how the Holobiont paradigm dismantles chemical dependency. In normal soil, you apply nitrogen fertilizer, soil microbes rapidly convert it into nitrate, and the rain just washes it away. It's a massive waste of capital for the farmer and causes terrible water pollution. But in a BNI-optimized holobiont soil, the plant roots naturally secrete inhibitors that block that rapid nitrification. It literally acts as a brake, keeping the nitrogen in the soil in a stable form that the crop can actually absorb over time. This drastically reduces the need for expensive, imported synthetic fertilizers. Section 6. Tech differentiation in next-gen agriculture. Let's zoom back out to the macro level and connect this microscopic BNI and Archaea science directly back to the business strategies of ag tech companies like T3. Right now, there are 3 potential market growth scenarios for agricultural biologicals: optimistic, base, and cautious. A massive hurdle for many biotech companies is the reproducibility problem, meaning a synthetic microbe might work wonders in one soil type but completely fail in another. T3's unique approach creates huge technical differentiation here. By utilizing Archaea, which are inherently tough, extreme environment survivors, they solve that reproducibility problem. So whether the market sees an optimistic 15% surge driven by AI or just cautious single digits, having a highly stable, resilient microbial product based on Archaea is the ultimate competitive advantage. So bringing it all together, we've gone from multi-billion-dollar macro market drivers all the way down to the microscopic control valves between Archaea and bacteria. And the main takeaway is this: deeply understanding and harnessing the natural diversity of the plant holobiont isn't just some neat science experiment. It is literally the most viable, rock-solid path we have to surviving extreme climate change, shrinking our chemical footprint, and achieving true, lasting food security. I want to leave you with this final thought. As regulatory walls rapidly close in and soils around the world continue to degrade, are we going to keep pouring capital and effort into the endless dependency trap of conventional chemical farming? Or is it finally time to look beneath the surface and invest in the Archaea-driven holobiont revolution? The future of agriculture is undeniably microscopic. Thanks so much for joining me for this explainer, and I really hope this transforms how you view the soil beneath our feet.